So parboiled2 is first of my large libraries that I was developing during Google Summer of Code. Hi. During Google Summer of Code project, and I released a pre-release version of it. I'm also involved in an initiative that is about porting parboiled2 library to JavaScript with help of Scala.js. So let us start with definition. What is parsing task is all about? In general, it is about telling whether input stream of chars or bytes have expected structure or not. So in my pseudo interpreter, I can put some input and ask for parser and if my input has a structure or not. And if it does, then I'd like to get the structure, maybe surrounded by some other interesting information. Oh, sorry. So what motivated us in general to create yet another library? Parboiled, the first version, was existing for some time when we started, and it was used by numerous of projects. And for technologies of that day, it was only possible to kind of interpret input rule structure. And when Scala Macros was introduced, it gave us an opportunity to compile rule structure to some more efficient code at runtime. And we also saved API to make it possible to migrate from first version of Parboiled to second easy enough. So what are existing projects using Parboiled? This is tools and libs that are dealing with different kinds of languages like CSS, Markdown, and so on. And I wonder if anybody of you are using Parboiled or Scala Parser combinators. Raise your hand, please. Oh, great. So I then strongly recommend you considering to migrate to second version of Parboiled, as it is much faster than Parser combinators and first version of it. And we defined some requirements to our new library. First of all, we required it to work entirely in Scala ecosystem to give a developer opportunity to use familiar tools like IDE, debugger, profiler, and so on. Java was not a point. So to communicate with Parboiled2 library, a developer need to write down some external interfaces to communicate it from Java. And it should work faster than the first version of Parboiled. It should be easy to maintain. So we needed a typed DSL that prevents most of grammar errors during compile time. And we needed to have it as few dependencies as possible. Some of existing alternatives to solve parsing tasks. First one is to sit and work hard to implement parsing with bare hand. The problem is that the price of change and maintaining is comparatively bigger than doing it with some well-typed DSL. You can use some of tools like Antler. The problem is that you should be familiar with its own ecosystem, debuggers, profilers, and so on. And you should also generate some output files, say Java sources, and attach them to your project. This might be a problem as well. The closest thing to our requirements was parser combinators from, say, Scala. But the problem with Scala parser combinators is that they are comparatively slow and produces lots of intermediate data structures. Well, regular expressions. Can they be used to make this parsing task? Apparently no, because they can't parse recursive data structures in principle. So data structures like arithmetical expressions, JSON, are impossible, would be impossible to parse. Compared to parboiled first version, second one is 10 times faster, has more powerful DSL, and has fewer dependencies in it. So my goal today is to give you a gentle introduction to parboiled library and to allow you to build and understand, say, calculator arithmetical parser from scratch. Core features of parboiled second is that it is based on parsing expression grammars. It is an alternative to context-free grammars, and this library has all necessary elements to solve everyday problems. Its DSL is flexible enough and type-safe that prevents you from most of errors during compile time. It does compile time optimizations that makes it really fast, 10 times, as I said, than first version. It has comprehensive parsing error reporting to tell you what went wrong during parsing of given input. It has one parsing phase and no lexer is required, so it makes it quite easy to use. And it also has small API that makes it easy to learn. To install it, you just use it like a simple Scala library. So you need to define external dependency in your build file. On Monday, final release was shipped, and now it has version of 2.0.0. And to use everything you need to build your own parser, you should just import this namespace. So let us start with simple parsing. That recognizes an input that starts with a character that is sequenced by B or C character. All base class of all custom parsers is parboiled parser. You should derive from it. And it only requires you to implement this kind of input that holds input that you provide to it. It is also convenient to define this input in constructor of derived class. So, and the implementation of toy parser is of every parser is a bunch of inner rules with a topmost rule that will be called against input. So what do I need defined a parser like this? What do I need to call it? I need to create an instance of it, call a topmost rule, and just run it. And the result by default will be instance of Scala util try. And if the parsing was successful, then it will be success with inner value. And in case of failure, I can extract this parsing error and use predefined util method to print information what went wrong during parsing. So let us take a closer look at what is happening while parsing in toy parser. When input line starts, it first calls left-hand side operator of tilde subrule and sets cursor position at 0. Then there is an attempt to parse A, and if it succeeds, then the parsing is continued with this alternative subrule. So A subrule is matched, and this causes a cursor to advance to position 1. Then alternative tries to match B, and it fails, so cursor stays at position 1. C subrule is successful to match, and cursor is moved to position 2. So the match is considered to be successful. But this only allows us to build so-called recognizers that are only telling you that input has expected structure or not. More practical use is to tell its, say, abstract syntax tree. And how can we do it? In parboiled2, you can do it only with help of value stack. And value stack is operated by typed rules. So rules by design are not taking any arguments and not producing any arguments. All they do are just moving inner state of a parser and might produce side effect. Say push some value on value stack or put or pop something from it. Push and pop value stack is a implicit is implicit data structure that is created per parser, and the rule can pops from it or push to it. And all interactions with the value stack are encoded in rule type. So I rule is a hlist from shapeless library that tells what number and what types of values should be popped off from the stack. And O encodes what should be pushed on it. In most cases, you can omit this type because they would be derived by Scala type system. But if you really need to write them, there is a predefined types that allow you just to put kind of aliases of it. So rule n is a type that just pushes n value on the value stack. Rule 0, rules of type 0, just does nothing with the value stack. Rule 1 just pushes a single value on a value stack. Rule 2 pushes 2 value, and you might notice that that corresponding hlist at rule grows from left to right. So as it does, and pop rule just pops a value from value stack. There are 3 kinds of rules in parboiled2. The first group is basic chars matchers that causes no side effects on value stack. They just keeps inner wheels of parboiled second rolling. Rules combinators are given to compose more sophisticated rules from basic ones. And parser actions, these are actions, kind of rules that actually makes changes to value stack. So let us take a look at simplest CH rule. It just matches a single char, and when you write rule of char, actually what happens is that implicit turns this character to a type rule, as rule can only contain arguments of type rule. Same story with string match. And if you try to put, say, integer value inside of rule, you will have compile time error, as there is no implicit defined in scope. Parboiled also predefines so-called char predicates that implements really efficient matching of character sets. One of these are digit and lower hex letter, and there are many more of them. And very useful char is end of input that allows you to match end of input in your rule. As for combinators, the most frequent used one is sequence combinator. It matches only if left hand side operator and right hand side operator of it are matched, are successfully matched. And its type is encoded properly. So consider these rules A and B that has type of rule 1 in string, int and string, meaning that A rule pushes int value on a string and B rule pushes string value on a value stack. So rule C, defined as a sequence of rule A and B, would have a type of rule 2 in string, meaning that 2 values would be pushed by that sequence. And other combinations of these subrules types are encoded in type of sequence rule. Alternative rule is a simple one. It just tries to match left-hand side operator, and if it is matched successfully, then it success immediately. Otherwise, the result of match is a result of match of right-hand side operator. Optional. Optional is a rule that tries to match inner expression E. It might match successfully or not, but option always matches. And the result type of optional depends on the type of its inner rules. Say if expression has inner expression has type rule 0 that deals nothing with value stack, then optional has rule 0 type as well. If inner type is rule 1, then on the value stack would be an option of type T. 0 or more and 1 or more rule combinators are obvious from their names. So 0 or more runs until E fails. And it always succeeds. 1 or more runs as well, E succeeds as well. But it succeeds only if E is succeeded at least once. And its types are obvious as well. Because, if inner rule is of type rule 0, then 0 or more and 1 or more would do nothing with value stack. And if it is of type T, then on the stack there will be sequence of type T. So, parser actions. We need a way to build abstract syntax tree. We can do it only with some actions that are predefined in parboiled second library. Simplest one is a push. It just pushes a value on a value stack, and it depends on type, and its result type depends on type of inner expression. If it's unit, then it does nothing with the value stack. If it is of type hlist, that means that on the value stack will be number of values according to type L, and otherwise there will be a single value T. Capture causes parboiled2 to match inner rule of capture, and if it succeeds, then the value will be pushed on top of value stack. So let us take a look at this rule. Capturing 0 or more digits causes this rule to be of type rule string. And if it matches successfully, then a string representing a sequence of digits will be on top of stack. This weird rule causes inner expression to in first parse try to match true, and if it is matched successfully, then push a true value of type boolean. But inner rule true was matched as well. So the actual type of this rule would be rule 2 boolean string. So boolean would be pushed first and string after that. This interesting arrow operator, it is most frequently used operator that can be called on any rule in rules DSL, and it adds action functionality to this rule. And the way it works, it causes to pop number of values from value stack equivalent to arity of this function. So these values then will be placed in arguments of this function. Looking at this rule foo that just pushes a string on top of the stack, I can call arrow operator and provide this lambda function. Because it has arity 1 of type string, during a runtime there will be an attempt to pop a string from value stack and to cast it to int. So the entire rule would be of type rule 1 int. I can omit this string type, and this will be derived by a Scala type system. I can even use underscored lambda expressions. I can demand 2 values from value stack and to merge them in a single value. So foo here will be of type rule2, and the result type will be of rule1. I can demand one value and produce no value by inner function. This will cause the value stack not to be changed at all, and the result result type of this rule will be rule 0. I can demand no value at all, but produce a value. In that case, it is just equivalent if I call a push rule. I can return hlist at inner function. This will cause all these values to be pushed on value stack. And the result type will be int, because here is an int, and double, because second argument is double. Another useful feature is using case classes in place of this function. So if I have a case class defined as follows, I can just place it in where a function is expected. And it is very convenient while abstract syntax tree construction, while parsing. Reduction rules is a special kind of rules that on the type level, it means that they don't change value stack at all. So consider a practical task to reduce input string to integer value 15. How can I do it in naive way? I can match a number and then more numbers and have a result type of int and sec. And to get a result, I just need to sum these values, pop these values from value stack and to sum them afterwards. To make it easier, I can define a reductor of that type. So what it does is that placed in argument of 0 or more and reduces two value from top of the value stack on to a 1. And this is why it is called reduction. Other types of rules that are also might be reduction rules are optional and one or more. So we have now all pieces of puzzle to compose our own calculator expression, arithmetical expression calculator parser. So first we need to define this calculator that extends parser. When we need to explain what digits and number are. Parents element is an expressions that will be defined later, and it is something that is surrounded by parentheses. Factor is something that is number or parents. Term is a factor that is followed by more factors separated by multiply or division operators. And we use reduction rule here. So as far as factors keep matching, we just merge most top values of value stack to a single one with corresponding operator. Expression, note that we need to define type of expression because actually it used recursively in this grammar. And the final top level rule, input line, that just an expression followed by end of input character. So we take so far and we understand some of the basic and most important elements of rule DSL in parboiled2 and what under the hood makes it so fast at runtime. Let us assume that rule is defined as follows. It does not encode interactions with value stack at all. In future, we have no error reporting here or recovery as well. But it is sufficiently enough to understand how parboiled works under the hood. Parser, beside input, also defines this rule macro and next char that returns next character from input and cursor pointing to current position of input. Parser macros object holds implementation of rule macro. Under the hood, there is so-called two-step rendering process. We need first to transform input Scala AST to intermediate representation called op3, and based on it we doing some compile time optimization, just generate efficient code to work at runtime. So quasi-code much. How can you define a rule? So when you define a rule like this, actually there is implicit, as I said. But what actually happens is that string method is called on current parser. And if you call tree on this rule, then you get a structure like this. And to get information that I'm interested in, I can apply it like this. And lots of boilerplate I see. Luckily, there is a quasi-quotes from Macro Paradise that allow me to match this R3 as follows. So I can produce op3 elements in a very effective and short way. Note that first of and sequence rule has op3 representations as well. And these are only some of op3 nodes defined in parboiled2. And all of them are derived from op3 abstract class that requires to define render method. And it is render method who is responsible for generating efficient code implementation. And so far, how can we define this char much? As I said, we need to define a render function, but what is inside? First of all, I need to splice current parser from context, as well as character from grammar. And all I need to do in the end just to verify that character from input is equal to a character defined in grammar. That's it. That's all required to implement char match. String match, naive implementation. So after splicing p and string from grammar, I just need to verify that all characters defined in grammar are equal to characters from input. The problem with this implementation is that it calls for all and makes a closure that makes it quite inefficient at runtime. More effective way is to explicitly define while loop that traverses our string in grammar. And I just need to verify in the end that the cursors in grammar string and input have the same length. So sequence is implemented very easy. We just need to verify that left rule is succeeded and right rule is succeeded and combine them with AND. First off is a bit complicated because I need to remember starting position to backtrack if left-hand side operator fails. But if it succeeds, then I return immediately. If it fails, then I should go back to a remembered position and try to match right-hand side operator. And the result will be the result of matching of that right-hand side operator. Benchmarking. So we took some of existing JSON libraries that are working on top of JVM and put 1 megabyte JSON as input. And we have a result showing us that that JSON parser based on parboiled second is about 7 times faster than a version implemented in parboiled first, but is a slightly more slower than other implementations of more efficient implementations of JSON parsers. So, in conclusion, I'd like to thank Matthias Donitz, that was my mentor for Google Summer of Code, Eugen Bumarko, and his team that made this all Macro Paradise possible, and all Scala community. And that's it I have for today. And if you have any questions, I would ask them, answer them. Thank you.
Yes.
Migration. Unfortunately, I'm not an expert of parboiled first. From scratch, from the first I saw that it was it has similar API, but unfortunately we have not yet instruction how to port from first version to second. So, but if you take a look at second version of parboiled, I think it should be obvious how to port it. Yes.
So the Scala parser combinators had a kind of functional approach where each parser would return a tuple or some value at the end of it.
Yeah, right.
And you're replacing it with a kind of equivalent value stack approach.
Yeah.
What's the advantage of using a value stack over simply having each parser return?
To avoid intermediate data structure construction. So when every function returns a value, it just should be collected by garbage collector somewhere. And value stack gives responsibility to manipulate intermediate data structures to a developer. That makes it faster at runtime. So, question? Yeah.
This might be a question more for Matthias. I'm using pegdown in my application to parse markdown. Pegdown depends on parboiled1. Is there a plan to move it to parboiled2?
To parboiled2. Matthias, would you answer? Yeah.
Sure. Yeah, so far pegdown is a Java library, right? So it's completely written in Java, and one major difference between parboiled1 and parboiled2 is that parboiled2 is Scala only. So there is no easy way to transition parsers that are written on parboiled1 on the Java side of parboiled1 to parboiled2, because parboiled2 is all Scala. And since pegdown is all in Java, we would have to rewrite everything in Scala, and then we could easily port it. There is a long-sitting pull request for pegdown that has a Scala version, but I never got around to actually merge that. So it might happen at some point.
Okay, thank you. Next question.
We have learned yesterday about Scala.meter. Are there any plans to have the macros adapted when it's out, or is parboiled2 kind of finished for a while?
As far as I know, meter is not released yet, right?
No.
So the answer is yes, I think. When meta will be released, and if it reduce code base and make it easier to maintain, of course we would migrate to it. So, more questions?
Yeah, I just want to try again. Essentially, the question is how much effort is it going from a large parboiled1 parser to a parboiled2 parser?
Mm-hmm. Matthias, do you have experience of porting? Yeah.
I have the same question actually about transitioning from the Scala standard library parser combinators. Are there common pitfalls?
Common pitfalls. There is no instruction, and I think there is. I don't know, person. Matthias, have you experience of porting from Scala something in Scala parser combinators to a parboiled2? What are pitfalls?
It's the approach is similar. The parsing approach is similar, but it's not quite identical. And the DSL is somewhat different, so it will take some migration effort. But you are about, let's see, it's like 100, 200 times faster. So it's worth it.
Scala parser combinators have this parser that given, well, depending on the input, given input, produces different parser for for consuming next input. Is it possible with parboiled2? Can it generate parsers on a fly during the parsing?
As far as I know, there is a dynamic feature in parboiled2 that allows you some... Yes, have you implemented dynamic?
The approach is in a way, well, it's a very good question, basically. The parser combinators, they generate the parser in the same phase as you actually parse. So there's no distinction between generating the parser and executing the parser. The parser is generated at the time the parser is running, right? And that gives you a lot of power, so you could, theoretically, based on the input, run completely different rules. Parboiled2, in the contrary, is a real parser generator. So the parser is generated at compile time. So the compiler translates your DSL into the actual code that matches the input at compile time. So if you want to do anything dynamically, that's much more difficult. So you don't have the same flexibility. What is implemented is that you can choose, based on the input, different things that you have precompiled. So if you have 3 different versions of your parser that you know before, right? But they cannot depend on the input. You can use the input to switch to one of those, but you can't dynamically change the rules based on the input, right? You can. It might be enough of what you need. We are actually using that in Akka HTTP for the HTTP header parser, because we have internally a long list of small parser stages, more or less, that each address one of those HTTP headers, right? And there are a lot of them. So we have like 30 different rule structures for each parser, for each HTTP header. So for the cookie header, there's one that parses cookies. For the date header, there's one that parses dates, and so on. So, and we only know the name of the header that we need to parse at runtime, right? So we need to use the name of the header to switch to one of those 30 different things. And that works nicely, and that's also very fast. Well, sometimes, depending on what you're doing, right? It might be that you are, I don't know, you're parsing a name, and then you want to take that name and match that name again, sometimes later or something like. You know, there are funky things that you might want to do that you can do with parser combinators just because you have those 2 phases combined. But generally, it's not what you need. So it's there's value in just getting rid of this phase that, you know, generates parsers at execution time.
So does that mean you won't be able to parse and validate, for example, XML in the same phase because you won't be able to match the second closing tag with the opening tag?
No, you can do that if you want to. But you could. It depends on what level you want to do. You want to do it, right? If you want to do it right in the syntax level, then it's hard. Then you would have to spell out all the tags that you want to have. But you can just generally match a tag, save the tag that you matched, and then try to match the end and compare at the end whether that actually is what you have matched before. And based on that, then either accept or backtrack. So that's all possible. Yes?
So that's really impressive. And if you could have a small question, could we go back to the performance slide?
This one?
That one, yeah. So, now, could you just briefly elaborate why there's a performance difference between parboiled2 and, well, organoid and the rest of the pack?
So parboiled1, in essence, is a kind of interpreter of input rule structure. So as far as I know, there are some runtime optimization, right, with bytecode that makes it a slightly more faster. But we can't just compile parboiled1 rule structure. So it just interprets it. And with the second one, we have a compiled code, and that's why it's faster.
Well, the question was why it's less, not faster than organoid, for example.
Faster.
It's not faster.
Maybe I can comment on that. There is still, I mean, we're using the macro infrastructure to generate the parser, right? So there are a few things that we can't do yet. For example, macros can't generate new members, right? You can't generate new methods. You can't generate new vals or vars or something in your parser. So we need to funnel everything through this one method that you define in your rules, right? When you, the example that Alexander showed right in the beginning, when you say def input line equals whatever, then the macro that sits there, the rule macro, translates the DSL into code of that method. And we need to channel everything through that method. So there are certain things that we need to do in order to support error reporting. So we have try catches in there that you wouldn't need if you are Argonaut, for example. Yeah. So there are certain things that we need to do in order to support proper error reporting and so on that make it a little bit less efficient than you would be able to do it if you do it by hand. But it's something that probably changes when the macros become more powerful. So the thing is, if you use parboiled2, you basically just, on a very high level, define the grammar that you need to match. And as the macros become more powerful and give us more features, we can implement more optimizations under the hood without you having to change anything. So you just upgrade to a new version, and it'll run 10%, 20% faster, and so on. And we still haven't really optimized it fully. There are certain things that we can do, but it's the macro infrastructure right now that prevents us from being completely as fast as Argonaut, for example, and JSON for as native. And also, you have to see that this is a very specific benchmark. This is a JSON parser that runs there, and it generates a JSON AST, which generates garbage or allocates stuff, right? If you compare it to Jackson, for example, Jackson doesn't generate any AST here. So this benchmark isn't really fair. The numbers that we show here is just a rough comparison for us. What's the difference? How do we perform, right? And if that's the numbers from if I run it on my machine with 1.7, Java 1.7, the differences are somewhat smaller or change. It also depends on the JVM. And those benchmarks, you all know benchmarks are tough, right? And this is not a very good benchmark. It gives us a rough indication, but don't take that really for granted. Like the performance for your personal grammars might be quite different from what you see here.